I'm going to talk about enabling modular reasoning of smart contracts in the presence of callbacks. This is joint work with Elvira Albert, Clara Rodríguez and Albert Rubio from University Complutense of Madrid, and Noam Rinetzky and Mooly Sagiv from Tel Aviv University. Our motivating application is smart contracts. Smart contracts are programs that sequentially process received events and modify state. Each contract state can be modified only by invoking the code of the contract. However, contracts can invoke other contracts. Ideally, we would like to be able to reason about each contract independently of other contracts. Smart contracts are used for financial applications for which correctness plays a critical role. In 2016, an attacker drained $50 million worth of cryptocurrency from a contract called the DAO. The attack was made possible by deploying a contract that, upon receiving an event from the DAO, invokes a callback to the DAO and breaks an invariant that the total stored currency covers user deposits. Here is a simple example illustrating how callbacks pose a problem for modular reasoning. Bank is a contract with two global state variables. B is for the bank's balance, D is for the total deposits. We would like to show that the bank's balance is always greater or equal to the deposits. The withdraw function allows returning the deposit by a call to ext. We assume the contracts run on a blockchain such as Ethereum, where any user has a unique identifier and is capable of invoking contract functions, such as withdraw. The function runs, and when it finishes, it commits the new state of the contract and of any external contracts invoked during the execution. The execution of withdraw is atomic in the sense that other users cannot invoke functions concurrently. But when the ext.call command is run, control is passed to the contract identified by ext. In particular, ext, whose code is unknown to us under the modular reasoning assumption, can also call bank withdraw function again. Suppose we have initially balance of 5 and deposit of 5. First we reduce the balance by the deposit so it becomes 0. Then we call ext, which invokes the callback to withdraw. For simplicity, we assume the callback's call to ext does nothing. In that case, b will be reduced by the deposit 5 again, becoming minus 5, and d will be zeroed. We return, and d is zeroed again. We saw a double decrease of b that led to the invariance violation, since b became smaller than d. Had we considered only executions without callbacks, we would see that the invariant holds. If b is initially greater than or equal to d, this must hold since both sides are decremented by d once. But the callback allowed unexpected behaviors that cannot be reproduced without using those callbacks. It can be concluded that callbacks make modular reasoning more difficult because we don't know how unknown contracts that are invoked affect our current state. However, in Ethereum, they are an essential part of the programming model, and disallowing them completely seriously limits developers. In this work, we're interested in proving that callbacks do not affect our ability to check other properties that interest us. In POPL 18, we introduced the concept of effective callback freedom, or ECF. A program satisfying ECF enjoys the following property. For any property phi of the program, phi holds in the general case, if and only if it holds on the callback-free executions of the program. Our previous example was not ECF. The property held on all callback-free traces, but was violated for a trace with callbacks. We want to allow callbacks in programming and in runtime, but not in ways that will break invariance of the code. Therefore, if we prove a contract is ECF, it will suffice to check just the callback-free executions. Here are two common solutions to the callback problem presented earlier. First is reordering of callback call and the state right. This means every callback could be executed after the original call ended, producing the same effect. Second is adding a lock. Thus a callback to withdraw will simply return without changing the state. Both of those solutions make the bank contract satisfy ECF. Our goal is to statically prove ECF and thus enable modular reasoning. To that end, we wrote ECFChecker, a sound tool that produces proofs for ECF and generates counterexamples that can be manually checked. Callbacks are a long-standing problem, especially in Ethereum, and ECFChecker is not the first in this problem space. Our technique is different from state-of-the-art security tools used in this space, by being based on analyzing behaviors of the code rather than its syntax. Here is a grossly simplified example. Contract C updates a global variable A to 0, calls some other contract, and then sets global variable B to 0. This code matches the write after a call pattern, since B is updated after the call operation returned. And thus, general-purpose security tools that check for this pattern report a potential callback vulnerability. This is sound, but in many cases, checking for this pattern will yield a false positive. ECFChecker will show that callbacks, no matter the order in which they are called, can be arranged in a way that produces an equivalent trace. From the same initial state, it reaches the same final state as the original one with the callbacks. ECFChecker gives a static proof that can be used to show, for every concrete trace with callbacks, how to build a new trace that is equivalent but contains no callbacks. In this very simple problem, there is only one interesting trace to consider, where the callback is called once. Since the final state is A equals 0, B equals 0, it's clear that we could execute the callback after the original call, without changing the expected final state. ECFChecker performs this check statically, without assuming concrete input or limiting the number of callbacks that can occur. It generates a constructive proof that shows what rearrangements of callbacks are possible. So while the proof itself is static, it can be used to convince why a particular execution trace containing callbacks can be simulated without them. On the other hand, if ECFChecker fails to produce such a proof, it gives traces that show callbacks can interfere in the state of the contract. In the general case, proving such a rearrangement exists statically and soundly is not trivial. We have the checked function parent call and the callbacks. We could have numerous nodes where callbacks can be called in the checked function, and each such call node potentially has an arbitrary number of callback calls. The idea is to compare a potential callback to a single code segment in the checked function, and to show that they commute. These commutativity checks are applied to show it is possible to move callbacks outside, either before or after the parent code segments, giving the same final state, but without callbacks. We have two basic building blocks for showing movement, commutativity and projection. Commutativity is easy to understand. We show the red code commutes with the blue code after it, so that if the red code happens after the blue code, the same state is preserved. Projection means that if a code segment has no effect on the final state, then we can simply ignore it. For example, if the red callback updates a variable x, but when returning the blue code zeroes it, without otherwise being affected by the update in the red code, then we could just leave the blue code. It is possible to combine projection and commutation to reason about complex code with branching. Here, the red code updates a global variable b, and the blue code either does nothing or reverts all effects. Revert is a special instruction in Ethereum. In this case, we can show by case splitting that if RC is true, then we can apply commutativity. But if RC is false, then it is movement by projection that holds. In both cases, the red callback can be moved to the right. From the basic operations of projection and commutation, we can build two trivial algorithms to check ECF. First is to check that indeed all call nodes appear after the writes. This can be done by checking that statically any callback code can always move to the right from any call node. The second trivial way to show ECF is to check for locks. If all call nodes and functions are properly protected by locks, it means that any callback code can project to the left of any call node. These two simple rules line up with the simple code fixes shown earlier for the bank example, but in more complex code, these rules may flag correct implementations as incorrect. In the paper, we elaborate on such examples. ECFChecker implements a generalized algorithm that does not assume movements of callbacks must be either to the left or to the right, but allows a mixture. The algorithm computes binary relations that are based on results of the commutativity checks. For each call node C and a callback F, if F is blocked from being moved to the left of the segment before call node C, then we say they relate by cannot left. Cannot right is defined symmetrically. In addition, we track functions that commute. In a call node, we must consider what happens if the callback sequence consists of more than one callback. So here we have f and g, and if g cannot move to the right, and if f does not commute with g, this means f also cannot move to the right in the same call node. From these relations, we can reason if the code is ECF or not. If there is a call node C such that f does not move to the left of it, and also cannot move to the right of it, then it cannot be moved at all. This means we could not find an equivalent callback-free execution with the same final state, and therefore it is potentially showing an ECF violation. Therefore, if there is a call node C and a function f that are both cannot left and cannot right, we conclude that the code is not ECF. The same applies for more complex callback arrangements. As we saw earlier, function commute information can also be used to infer the cannot left and cannot right relations. We saw that if g cannot move to the right of c, and f does not commute with g, then f also cannot move to the right of c. Hence, if we also find out that f cannot move to the left of c, we again reach the conclusion that the callback f is stuck in c and cannot be rearranged. We achieve soundness by considering function commutativity, because when functions commute, we can show that the movement is possible in any callback ordering. In the paper, we elaborate more on how a real example was proving ECF using this technique. The implementation of ECFChecker is operating on the contract's low-level EVM bytecode, which allows us to check any contract deployed in Ethereum. We decompile the bytecode and first split it to functions, since the Ethereum virtual machine has no notion of functions in contracts. Then we locate all places in the code that constitute a call node and extract the function segments accordingly. The algorithm runs separately on each function's partitioning to code segments. Now the algorithm uses an SMT solver to check for movement using projection and commutation for pairs of segments, where one is a segment of the checked function and the other is a function executed as a callback. From the results, we fill in cannot left and cannot right. We also compute full function commute relation and update cannot left and cannot right accordingly. If at some point we find a call node C and a function f that are both in cannot left and cannot right, we report not ECF. Otherwise, at any call node, any callback is not blocked from moving in at least one direction, and thus we're able to return ECF. In the paper, we elaborate in greater detail on the fine details of the check, such as handling call nodes that occur in loops. We also show how to make it more precise by including the segment joint operation. We applied the implementation on top contracts from Ethereum and analyzed them. A contract is ECF if all its functions are ECF. These are the results by function. We see that most functions do not contain even a single call node and are therefore trivially ECF. Out of the functions that do contain call nodes, most were proven ECF. But for 133 functions, we could not prove ECF, and I will briefly explain the reasons. For the great part, violations came from our highly conservative choice of call nodes. Any external call of any type is a call node for us. Another source was the modeling of the low-level EVM bytecode and its data structures that is over-approximated. 18 instances we could not manually check due to lack of source code. 11 are real false positives. We manually analyzed every instance here, could be simulated without callbacks, but our generalized algorithm is too strict for proving it. We explore that for future work. 18 are real ECF violations that could lead to bugs in the contracts where they were found. Running times of analyzing functions were usually pretty quick, and less than 5 seconds, because not in all cases we needed to employ SMT to reason about commutativity, but some codes were much more complex and took over an hour. To summarize, we found that smart contracts is an interesting domain for static analysis where it has benefits, and ECF can be checked effectively. This means we can apply modular reasoning on contracts that satisfy ECF. We've also shown that commutativity checks on small code segments can be used to prove a complex property such as ECF. In the paper, we also show how the user can help the analysis be much more precise with the special notion of callback invariants, invariants that hold on call nodes. Thank you for watching.